I am pleased to introduce to you Dr. Luke Wilson, who is the Chief Data Scientist of the HPC and AI Innovation Lab at Dell. He joined Dell Technologies in 2017 after 12 years at the Texas Advanced Computing Center, TAC, where he worked on developing next-gen AI-based techniques for performing parallel computations, as well as a number of distributed computing infrastructure tools. And prior to the session today, he was telling us how he used to attend TeraGrid meetings and the like. So probably you guys already know him. So Luke's topic for us today is HPC gives computers a voice. Luke, the floor is yours.
Thank you, Ruth. And I just want to say it's a great opportunity and pleasure to be able to come back to this community and speak to you in this forum. Like Ruth mentioned, I started working with this community 10 years ago. TeraGrid 10 was my first event with this community, and through the TeraGrid years, the Exceed years, and now PEARC, it's been a pleasure to grow with the community and watch the community evolve. So my talk today is about work we're doing in the HPC and AI Innovation Lab at Dell in some of the non-traditional areas of artificial intelligence. We're concerned about more than just doing image recognition and doing benchmarks. We're really concerned about showing the real power of artificial intelligence and how high-performance computing infrastructure is making all of those advances possible. So if you go to the next slide, just a quick overview of the HPC and AI Innovation Lab. For those of you that don't know, Dell Technologies is really more than just a server network storage provider. We're also doing a lot of software work. We're doing a lot of research in the space, especially in HPC and AI. We have a very large facility in Austin where we're doing really these three basic things. We're developing best practices around the use of our servers and storage and networking. We're doing a lot of industry-focused research with our customers and technology partners around advancing the state-of-the-art in simulation, in machine learning and deep learning. And then we're trying to get out there and contribute back to the community. So don't be surprised if you see more of these types of talks at conferences going forward. We really want to be out there talking to you as members of the research community, getting feedback from you, working on developing partnerships and collaborations so that we can help you advance the state of the art in these fields and achieve your goals. So next slide. So what I'm going to talk about first is just a little pat on the back for the HPC community. We go to the next slide. We all know most of this. This has been kind of high performance computing and advanced research computing's bread and butter for the last 30 to 40 years, solving the equations that govern the natural world is something that HPC has done forever, from helping to interpret data that was coming out of the Black Hole Observatory. You can see a picture of the M87 galaxy there. Was the first optical image of a black hole ever produced. All of that data processed, of course, on HPC resources, from developing molecular dynamics models of very small viruses, doing all sorts of computational fluid dynamics for aerodynamic simulations for weather forecasting, and doing things like going back in time and looking at the evolution of the universe. These are all things that HPC has done for decades and does really well. So next slide. But what HPC is doing now, in addition to just simulation, we're looking at using HPC as a tool for very large scale approximation. In this case, approximating the capabilities that we have as humans to do interpretation and reasoning of the world around us, from being able to classify objects and images, whether that be video of people walking or driving down the street, to classifying potential pathologies or abnormalities in medical images, to being able to intelligently decide what to do if you're an autonomous car, for example. How do we decide when to drive through a crosswalk? How do we decide when to turn left, when to turn right? Make sure that oncoming traffic is not going to run into the car. All of these things that we would normally associate with a seasoned driver. How do we get the computer to do those types of things? And then lastly, something that is a little less visually based. There's many more examples, but the one I'm going to talk to you about today is voice. How do we communicate with systems? Human to system communication, using the communication method that is most natural to humans, which is using hearing and spoken word. So if you go to the next slide, what we really want to do long-term is create these conversational-like experiences with computers. So if a person needs to make a support call, for example, normally they would expect to talk to a customer support representative on the other end of the line, and they expect that interpersonal communication. But what we'd like to see is if we can build a system where instead of talking to a customer support agent, they're really talking to a machine on the other end. But we want that conversational experience to feel seamless. We want the customer to feel as though they're talking to a human being on the other end. Next slide, please. And in order to produce this, you actually have to connect multiple AI models together to produce this end goal of seamless intelligence, from converting the customer's voice into text, possibly translating that text from one language to another, having an intelligent conversational agent make a real response, converting that back into the customer's language, and then finally synthesizing a voice to convert that text into an audio file that's transmitted over the phone, and do this all extremely quickly and seamlessly, so that from the customer's perspective, it sounds as though they're talking to a human being. When in fact, there's no one on the other end of the line. They're literally calling a data center that's handling all of this processing. And at Dell, we've been working on many of the components of this pipeline. We presented a paper at ISC last June on the language to language translation part, working on how to scale those language translation models to much larger node counts. They were very difficult to scale before, and we worked with our technology partners at Intel and AWS and our research partners at Surfsera in the Netherlands to develop a much more scalable approach for building these types of translation models. But today, what I'm going to talk to you about is the voice synthesis, so this last part that's highlighted here, which is another interesting problem. It's even more complex than the language to language translation part. Next slide, please. So what we really want to do is be able to accelerate the creation of these voice synthesis models using high performance computing infrastructure. And the reason is that they're very complex. So if you go to the next slide, creating a voice from a model, from a text input is very difficult. It's a two-step process where you're taking input text, you convert it into this format called a Mel spectrogram, basically giving you an intensity readout of the audio of what the person should be saying, and then translating that into an audio waveform. And for the last part, we use Google came out with a particular algorithm called WaveNet, which converts those Mel spectrograms into seamless audio. Instead of using phoneme stitching, like what we're used to when we call trees or things like that, where you have clips of a voice actor that are stitched together to produce the appropriate words. These generative learning models like WaveNet actually create a very seamless, continuous waveform that is less distinguishable from a natural human voice. But we have to get there first. So we have to take that input text and convert it into the Mel spectrogram. And what we've done is we've actually used models that were produced originally by NVIDIA, Tacotron 2 and WaveGlow, in order to produce this end-to-end component. So if you go to the next slide, the very first thing we want to do is use Tacotron 2 to produce input text, to produce the Mel spectrogram from the input text. So next slide, please. And go ahead and advance this two times. So what we've done is we've actually looked at how long it would take to run this on a single server. We ran it on PowerEdge R7525, so that's one of our AMD-based building blocks. So 2 AMD EPYC Rome sockets, and then we put 2 NVIDIA V100s in it. And we've trained this model that produces these Mel spectrograms from text And it takes a considerable amount of time to train. So 11 days to produce a reasonable model that can generate these Mel spectrogram images. In some situations that may be fine, but we're always in the advanced research computing community, we're always worried about getting the time to solution down as low as possible. So if we go to the next slide, we tried the same thing again on 16 servers. So this time we've got 32 NVIDIA V100 GPUs all tied together with Mellanox 100 gigabit per second EDR InfiniBand. And what we were able to do is show that this model, which is written in PyTorch, there's some native support for MPI, but we had to do a little bit of optimizing on that to make sure it would run properly in parallel. We were able to get the time to train from 11 days to 11 hours. So a substantial improvement. It's always nice to be able to train a model in a single day rather than waiting 2 weeks for something to get accomplished. Nothing really special, just adding a little bit of parallelism to the problem helps to dramatically reduce the time to solution. So next slide, please. So that takes care of the first part of this. So hit next, please. The second part is actually converting that Mel spectrogram into an audio waveform. Next slide, please. This part is even harder. So the way that you convert a Mel spectrogram into an audio file, you're actually performing something akin to a reverse Fourier transform in order to change that spectrogram into an audio file, into an audio waveform. But in terms of building a neural network that can approximate this process is very, very difficult. So on that same single R7525, producing a model to generate waveforms took us nearly 3 months. So 82 days to produce a model that was capable of producing reasonable audio output from those Mel spectrograms. And we believe that that's completely unwarranted. There's no way that we would expect most people to wait 3 months to generate a single model. So if you go to the next slide, we took the same setup we had before, those 16 7525s, and we were able to reduce that time to train down to 4 days, a little over 98 hours of time. So again, a dramatic improvement. And if we were to sum it all together, taking both parts of the pipeline from the conversion from input text to Mel spectrogram and then the Mel spectrogram to audio waveform, if you go to the next slide, we will see it all together. On a single server, 93 days to do the entire end-to-end process with just a little bit of parallelism. 16 nodes, not considered a big cluster anymore. Definitely something that a research team at a university could have in their little data center, or something you could easily request time for on one of the national resources. We got that down to 4.5 days. So a substantially better result in terms of time to train. Same quality solution, just by adding a little bit of scale out parallelism. So if you go to the next slide. So the question always is, great, you can train these models fast. Parallelism is always nice for that. But how does it actually sound? How does it actually perform? Because when we do AI, we're looking at two things, because we're not solving the fundamental equations that govern the universe. We don't necessarily know what the result is going to be when we finish training the model on the other side. And so the question always becomes, how good is this approximation? How good is this simulation of some human characteristic that we're very used to experiencing in day-to-day life? And so what we've done is we've actually stitched together some training samples, some audio, and this is the system saying the same phrase over and over again throughout the training process. So starting very early in the training process when you hear nothing but white noise, and then continuing through the process of it teaching itself how to approximate human speech by looking, learning how to space out syllables and words, learning how to, give proper intonation, and eventually learning how to speak in a reasonably well-formed human voice. And if you think about it, the process is relatively remarkable. We're training this model in 4.5 days to teach itself how to speak. For a human being, this process takes years. So, just comparing it to what humans have to do in order to teach themselves to read and speak versus how the computer does it, it's a pretty remarkable process. So go ahead and hit next and it'll play through the clip.
Anywho, the 38 Hello world, this is my voices. Hello world, this is my voice. Hello world, this is my voice.
And so you can see that over the course of just a handful of passes through the data set, in this case, we only trained it for 650 epochs, the system was able to go from generating nothing but random white noise to generating a fairly realistic sounding human voice. And all the while learning a lot of the odd kind of idiosyncrasies of the English language. We have lots of situations in English where the same combinations of letters in different words have different sounds, which is always confusing for pattern matching and approximation systems like neural networks. But just through an enormous number of training samples and training samples of different sizes. So the training data set for this model actually includes pairs as small as a single letter and a single sound to blends of two letters, all the way up to entire words and phrases. So that breadth of variability in the training data set allows the system to give a very good approximation of how a human being would sound if they were actually speaking and reading the words that you give it. So before we end, I wanted to take a few minutes to just summarize kind of what we've been doing in the lab. So on the AI side of things, we've really been trying to push the state of the art, showing what is possible with these approximation techniques, showing what is possible with these simulations of human function, as we like to call them. I mean, we're not generating what anyone would call general intelligence, and we won't be for any considerable length of time. But these narrow intelligence models, where we can simulate a particular function, even though those particular functions might need several different sub-functional models in order to glue them all together and make something reasonable out of them, have yielded tremendous advances in what we, in the way we think of what computers are capable of. Computers have come a very long way in the last 6 years. They're more than just enormous calculators now. We're actually able to interact with them in a very natural way, not just solve the equations that govern the natural world, not just build a simulation of the world that we already understand very well, but build models that are reasonably good at approximating the fuzzier, messier aspects of human existence, the way we interact with one another, the way we interpret the world around us. And I'm just going to close by letting the computer speak for itself. So go ahead and hit the next slide.
High-performance computing has given computers more than just a voice. It has given computers the ability to interpret the world around them.
If you have any, if you want more information, you can check out the Innovation Lab website at delltechnologies.com/innovation lab. And we publish all of our research work and papers at hpc@dell.com. So please feel free to go check it out. Send us an email. If we're not already working with you, we'd be happy to put together a partnership. And if we are already working with you, let's do something new. So thank you.
Thank you, Luke. That was really interesting. And we do have some questions coming in, but I have to ask the first question. Okay, you opened with talking about seamless intelligence. One of the things I love about talking to people, not the computer generated voice at the other end, is I don't find human intelligence seamless at all. We make mistakes. We mess up our words. We mispronounce. We do things. So surely having some error, I mean, how do these models take into consideration actually how people talk, not just the words, but those errors are introduced inadvertently or deliberately when we speak. So can you say a little bit about that?
Sure, and you can tell when you listen to one of these voice models that it produces errors as well. These models are approximations of our own approximation system. So the brain itself, I mean, if you really think of it from a connectionist standpoint, is an enormous pattern matching approximation system. We don't have perfect answers for anything. We're not a deterministic system like a computer. So we make mistakes all the time. And these models are designed to mimic that. So we are approximating this imperfect world on a deterministic system. And so I feel the same way. I feel very uncomfortable when I listen to something that sounds completely perfect. Same thing with computer graphics. And I don't know if anyone else has experienced this, but sometimes when I'm watching a video game, especially these more modern video games or modern computer-generated movies, if the rendering is too quote unquote photorealistic, it feels awkward. It feels artificial. The more realistic it gets, the more artificial it feels because it doesn't match the imperfect world that we're used to living in. Do I think these models will ever become perfect? No. And I think it would be wrong to try and make them more perfect because then they really become uncomfortable for us as humans to interact with.
Great. Thank you. So a bunch of questions here. Are Dell's improvements to PyTorch available?
So our improvements were not to PyTorch. We were just making modifications inside of the model, inside of the way we were scaling Tacotron 2 and WaveGlow.
Great, thank you. Is there a time difference in generation time based on different languages?
Well, that's a great question. So the model we built was really only designed for English. And we've wondered about the same thing with language generation models, and several teams at groups like OpenAI and different large-scale research teams have looked at the question of whether or not different languages require different levels of effort in order to generate good approximation models for. They found in the language translation case, it's not necessarily a problem. In fact, most language translation models require very similar time to train, time to converge. I have not looked into the literature or explored it with the voice synthesis models, but I think that's a great question, a great place to explore how building different voice generation models for different languages would change the training time, because obviously you have different sounds in different languages, especially with various different root languages. So I think it would be an interesting place to explore further research.
There's some questions here about your model. What was the model you used, and how big were the training and testing sets?
So the model, we used two models. So we used Tacotron 2 from NVIDIA. It's on GitHub. And we used WaveGlow, which is also an NVIDIA model. They're not enormous models, when compared to things like GPT-3, but they're not trivial in scale either. So they, multi-million parameter sorts of models. And so there's not, so you can go check them out yourself. You can go to the NVIDIA GitHub and grab them. We happen to use them, for us for our work because the engineers at NVIDIA had already done a great job of building them. We're not going to reinvent the wheel when we don't have to. And then we were able to use them on these AMD based systems to do the work.
Okay. So Stefan Thiel writes, going from 11 days to 11 hours of training is impressive, but it's still 11 hours. What do you think is currently limiting the training speed? CPU, GPU, memory speed, network, fast storage, all the different components that Pranav talked about. So what do you see as the limiting factor?
Well, I think, especially in a lot of these scaling studies that we do, you have to go back to, I think it was a Seymour Cray quote, but I could be wrong. It said that supercomputing does nothing but turn compute-bound problems into I/O-bound problems, and that's really what we're doing here. We're adding compute so that everything we do ends up being an I/O-bound problem. It's just that we can't load and process data more efficiently. All we can do is data parallelize the process by adding more compute nodes. And eventually, whenever you're doing strong scaling, Amdahl's law will catch up with you and you will run out of components to parallelize and you'll be stuck with the data load as your limiting sequential factor.
Sure. We have time for one more question, I think, before we wrap up. And this is an interesting one. Have you looked at how this technology can be used to help people with speech impediments?
So we have not specifically looked at this in terms of what we can do to help those with various speech impediments or that suffer from structural mutism or anything like that, where they're unable to speak. I am sure there are teams out there, especially at the research universities and research computing groups that either are working on this already or that would love to explore this. And in terms of doing those types of things, we would be happy to partner with a group looking to figure out how to do that efficiently and put that kind of infrastructure together.
Nice. Well, thank you.